Hi and welcome to Unit 2, Topic 3, Video 13, where we start to look at our main context of matrices. So you've worked through some work on matrix arithmetic, including multiplication, and we've talked about the context of solving a simultaneous equation, which is kind of like our minor context. And the syllabus then draws us towards linear transformations of points and shapes. And it's important to recognise this points and shapes bit here. In my experience of this, people are going to be confused when I swap between points and I swap between shapes. So I'll try and be really specific about it, and hopefully you'll see what we mean. Learning goals, success criteria there. As always, let's have a look. So let's consider matrices and the Cartesian plane. A coordinate can be written as a column vector, which is also a 2x1 matrix. So we could represent a point. This is one of those points by a coordinate there. A comma B becomes AB as a column matrix. If we transform a coordinate or a set of coordinates, then we move each original to its image under the transformation. Now you might consider pausing occasionally here to write down some of these definitions. It's definitely not worth writing down verbatim what I've got written on the screen. It's worth writing them down in your own understanding. Maybe you'll watch the whole video and then you'll go back and summarize some of these main definitions. So if we transform a coordinate or a set of coordinates first of all, so we have a coordinate or a set of coordinates, which is a shape. So obviously if I define 4 coordinates, that might be a square or a trapezium or something like that. And so we can transform shape just by transforming a whole bunch of different coordinates. We start with the original and then we end up at the image under the transformation. So when you do the transformation, you move from the original to the image. XY goes to X dash Y dash. So we use these little dashes to represent the image. And we can write it as a column matrix as well, rather than a coordinate. A transformation in geometry or in functions can be a translation. So this is going back to your work in math methods. If you translate geometric shape or a function, you shift it up or down or side to side. A dilational enlargement, so that is when we grow it. Either a dilation typically is in the x-axis or the y-axis in one dimension, and enlargement usually is in both axes at the same time. But we could also rotate a shape or a function, but we don't do much with functions in terms of rotations, or we could reflect a shape or a function. So we're going to talk about all of these and more. We're going to be talking mainly about what we call linear transformations. Some of those main transformations do break out of the mold, but most of them are going to fall into this one single mold that we're going to talk about now. So if the coordinate x is taken to, let's say, some number of x and some number of y, it is a linear transformation of the original coordinates. Then we get ax plus by, cx plus dy, which means that the transformation of, let's call this coordinate x, so there's another dash there, goes to the image coordinates. So the original goes from x to x dash, x goes to ax plus by, y goes to cx plus dy, and it can be written as this combined matrix, ABCD times xy. Then ABCD, which I'll highlight now, this is our transformational matrix. It does stuff to x and y. Now I don't want you to be too worried. ABCD is quite complex. What we're going to find is actually, when we get further in the video and look at some of the basic transformations, most of them are just a simple variation on the identity. So the identity being 1, 0, 0, 1. Well, if we do 2, 0, 0, 1, for example, that's just a dilation in the x-axis. And it does nothing else. So we're going to break this down into really simple transformations, and then we'll talk about combinations of transformations a little bit later on. So example 1. If a linear transformation is 2, 1, 3, 0, what's the general transformation? What's the image of the point 2, 1? And what is the image of the unit square? So this is where we're talking about the image of a point and then a shape. And I'll show you the difference of this. So first of all, the general transformation is, what does 2, 1, 3, 0 just do to any coordinate? That means we're going to multiply it by this coordinate, x, y. And this will be equal to 2 times x, 1 times y, 2x plus y, 3 times x. So what it's saying is that whatever the x coordinate was, it now goes to a new coordinate, a new x value of 2x plus y. And whatever the y coordinate was, it goes to a new value of 3x, whatever x was. So let's have a look at what happens with this coordinate here, 2, 1. So we have 2, 1, 3, 0, and we multiply that by 2, 1. And we can either use this generalization or we can just do the multiplication again. Basically, we get 5, and then we get 6. So if I was to draw this, I'll do a really rough, I know I don't have any negative quadrants to worry about. 2, 1, which I might say is here, it goes out to 5, 6. 6 is a bit of a pain, up to there. So this is, we'll call it the point A, and then this is A dash. So this transformation takes it away to there, which is really good. Okay, so that's part B, and that was all it's been asked us to do, and that's the move that's happening. It's pretty boring with a point. Now we talk about the unit square. Now, I'll show you this the long way, but there is a shorter way of doing it as well. So the unit square is made up of 4 coordinates, which I'm going to write as column matrices. So the coordinates are 0, 0, which is the center, 1, 0, 0, 1, and then 1, 1. And so we'll actually have a look at this image, but let's start. Give myself a bit more room this time, just in case. This is there, 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 and there. That's my unit square. So if you ever see the unit square, that's a definition of the unit square. Now for the second part, I just want to make note that we could write this unit square as a single matrix. 0, 0, 1, 0, 0, 1, 1, 1. And we defined all the coordinates into one single matrix. So I'll do the working for blue down the side here. The working for black is just to look at each individual component. 2, 1, 3, 0, multiplied by the identity. All that's equal to 0, 0. Oh, not the identity, sorry, the origin. And then we have 2, 1, 3, 0. This gets a bit monotonous. 1, 0. And that's equal to 2 times 1. 1 times 0 is 2. 3 times 1 is 3. Okay, so there's my 4 image coordinates. I've got the original coordinates. They are all found here, and the image coordinates are all found there. So I'm going to go through now to define these positions. This one, this blue, will actually goes to itself. So circle to represent where it started, X to represent where it is now. This green one started at 1, 0, which is here. It now goes to 2, 3, which is 2, 3, it's there. Oh, I'm going to use a cross. Okay, and then this orange one here, it started at 0, 1, which is here, and it went to 1, 0, which is actually there. So that's interesting. And then we've got this pink one. 1, 1 started here, went out to 3, 3. And so we've got this new shape now, which is a parallelogram. So this actual transformation now is moving to the parallelogram. Now, it's a pretty complex transformation. It looks pretty simple, 2, 1, 3, 0, but it's actually quite complex. And it goes a little bit beyond what's happening here. We'll talk about this later, but that 2, that's actually a dilation. This 3 is kind of a reflection, which is why this point flips over the other side there. This 0 does nothing, and then this 1 is kind of part of a reflection as well. So there's some complexity in here, but you can see that actually just calculating the coordinates and the image coordinates is pretty easy. Now just the last little bit, we could do this a little bit simpler by just going 2, 1, 0, 3, 0 times by the whole shape in one matrix. So our dimensions, you can see, are correct. So this works, and we'll just go through 2, 1, 3, 0. This is equal to 0, 0, 2, 1 becomes 2, 3, 2, 1 becomes 1, 0, 1 becomes 3, 3. And you can see each coordinate there, 1, 2, 3, 4. And in terms of colors, that's that one, this is this one, this is this one, and this is our pink one here. So you get the same result, but it does save us a bit of time, which is always nice. Okay, well this is the end of this video, just showing some of those transformations. Hopefully it's made sense. Definitely go back now and make a note of some of those definitions. All the best.